feel free to ask any questions at any point in between. Let's keep this more interactive. So my research interests span across 3 topics. One is video and image generation, improving the generation quality, making them more efficient. But also there is a core interest in understanding how these models understand, interact with.
Can you share it because on the call? I think only like right now screenshot so that people online see the.
Oh, okay. Yeah. No. Please.
Yeah, now it's now live.
Okay, perfect. Okay. Is there a way to make this? So that it's less distracting. Okay, so understanding how these models reasons and by using interpretability tools. So here is my research group with a few PhD and master students who are driving this agenda of improving the reasoning, generation, and quality through interpretability tools. So here is where we are at this point. I don't know, some of them. Image and video generation models are becoming extremely photorealistic. They're becoming very pervasive. We are at a place where it is getting really difficult to distinguish between an image that is AI generated versus a real world picture. Not just in the world of vision, of images and videos, we've also seen LLMs and multimodal models doing really good at very complex reasoning tasks, such as complex math problems, solving really complex challenges in the domain of robotics and many other topics. So bringing the discussion back to vision, 2 years ago, 3 years ago, these were the questions that we really cared about. How do we make these models? How do we improve these models such that the generation quality is really good, the images or the videos are photorealistic, and it's not like you look at an image and a video and you can't like immediately tell that this is AI generated. So that was the goal of the field 3 years ago, but a lot has changed. All of these we have checked out. Now images look extremely photorealistic. This is one of my favorite generations where just the reflections of the light on the bubble gum is perfect. This again, like the interaction with the fog and the trees and the shadows is also like extremely photorealistic. So we've checked these 2 boxes by and large. So that brings an existential question as to what should we care about, because when these 2 things are already checked out, turns out there are a lot of other things that still require attention, that still require improvement. Here are just some of those many things. Even though we are getting very good at generating short form videos, getting a longer form videos is extremely still challenging. The temporal coherence is one big bottleneck at this time, where you want the same coherent action to be smoothly generated over time. Controllability is also a very big thing. You have really good tools, but making the model listen and follow the exact prompt that you're providing continues to be a challenge. Safety and efficiency, again, like they continue to be major bottlenecks. So good news for all of us in this room, there are still many exciting, challenging projects that we can, directions that we can continue to push. So this talk will focus on two aspects. One is on reasoning, understanding and identifying the gaps in present-day models, and also understanding their inefficiency gaps and trying to mitigate and make them more efficient. So let's dive deep into the reasoning. One question that drives the agenda of in my research group is, how do different modalities interact and assimilate information and learn this semantic concept? So we know we consume information from several different modalities: vision, language, audio, touch. And in the case of models, they do the same. We now have quote unquote multimodal models where mostly tokens are just appended and fed into a decoder. Is that the right way to assimilate multimodal information? Has been the core focus of our work. So this is one of my favorite examples that tells.
Have a look at this. What do
Hopefully
you
it's
hear?
visible.
Ba, 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 ba,
But look what happens when we change the picture.
ba, 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 ba.
If possible, I want you all to close your eyes and listen to the same thing.
And yet, the sound hasn't changed. In every clip, you are only ever hearing bar.
If the effect was not obvious, the audio has always remained to be ba. It's the visual component where the person is silently mouthing ba, and we have this auditory illusion that the person is actually saying fa instead of ba. So this example has driven like a couple of directions or projects that I'm going to talk about, where we as humans, we're so robust, we're so good at assimilating information. If we can be fooled this easily, what happens when we present similar information to multimodal models? So we're focusing on three modalities: vision, language, and audio. This is our baseline example where image, it's a red apple. Uh, the caption associated with the image also describes there is alignment. And let's say there is an audio or a spoken language of someone saying this is a red apple. All three modalities aligned. This is the good case. We'll start by tweaking one modality at a time. In this case, let's say we tweak the caption and say this is a B. The rest to remain the same. So even perturbing one modality does cause misalignment between vision and language and audio. So what happens to the reasoning of MLLMs when we present it with this scenario? When we ask what's happening in the image, can it still focus on the vision element, which is not corrupted, or does it get distracted by the distracting caption? So that's our question. And you can see how we can like come up with multiple like combinations where we perturb the audio, keep the vision and language the same, and see what happens when we probe the models on different tasks. So let's say this is our video. It's a loudly barking dog. So now, if we are asked what object best describes the audio in this image, fully most of us will agree that it's the sound from a dog barking. And we close our ears and say, just look at the video, no audio, tell me what's happening in this. And then we'll say, yes, it's the dog. And so that's an aligned sample. And here is an example of a misaligned. So the object is a cache register. If some of you are not familiar, but the audio is that of a printer. And this is something that we can parse out easily by when we are asked to say, just focus on the audio and tell me what is the object that's making that sound. And just focus on the visual component and tell me what object you see. So these are the probing questions that we asked humans, and we asked a series of MLLMs. Is the setup clear? Okay. Why study this? Well, there are benchmarks that exist out there. They also do audio visual interactions, but they don't do this targeted one modality perturbation at a time and see which modality is the models are more reliant on. And they also don't give us the fine-grained information about this. When I ask an audio question, it's getting distracted by the video distractor class that you provided. So this benchmark that we put together, it addresses these finer grained issues. We call it multimodal alignment benchmark. So three rules in mind when we were putting together this evaluation data set. There has to be one single sounding object. So there has to be one primary sounding object, just to make it as easy to the model as possible. And there has to be one single source of audio. So it cannot have a dog barking and a cat meowing somewhere else. Just we want to give the model as clean a signal as possible. And then the object should be the primary focus in the video. It cannot be somewhere else. So just giving the model the cleanest signal, giving it the best chance to do a good job, essentially. So this is our baseline case that we talked about, all three modalities aligned. Great. Then this is the other case where we only modify the audio components. The video has a bell ringing. It's a smaller image, but then we've added the audio. We've removed its original audio and added a dog barking sound to it. So it's the audio that's perturbed. In the third case, the video and audio are aligned. It's the text that is slightly misleading. We insert just a distracting text of an object that's not present in the video. And the fourth scenario is this is to stress test the long context reasoning of these models, where we just inserted garbage text and try to see if that again distracts the model or if it's resilient to these distractors. So 658-ish aligned videos and misaligned different comps. So this is the evaluation part, hence slightly smaller scale. And we have about 5,000 and we have 5,000 question answer pairs. So we've studied a suite of models, but I'll show maybe a best and worst performing one. Just to jog everybody's memory, we have a visual prompt where we tell the model focus only on the vision and name the primary object that you see in the video. So in that case, in visual prompt Quen 2.5, when the video and audio are perfectly aligned, it had 76% accuracy, but when the audio is perturbed, video stays the same, but we are still asking only a visual question. That still led to a drop of nearly 20%. And then let's look at the audio prompt. Audio is the case where we are asking the model to focus on the audio and predict the sounding object. And here, to start off with, it has a low performance. It's at 46%. But then when we give the perturbed audio, the intent is that it will predict the perturbed audio class correctly, but even that, it was struggling. So three key takeaways. One is that there is a drop in the performance when modalities are perturbed or misaligned. Audio starts off, even the baseline has a poor performance, and it further takes a hit when we add distracting audio. So this is an indication that there is integration. The models are trying to integrate different modalities, but in the event of a conflict, they're not able to separate out which one to focus on.
maybe more like a comment, like you said, I think it could almost be good news, because sometimes I'm concerned with models that they're ignoring some modality like fully, like audio. So at least we know like they're using the evidence and not just like relying on a single modality.
Yeah, wait for the next slide, which is Gemini 2.5, where same task, same data set. This was good news because we perturbed the audio, but the model remained robust. There isn't a hit in the performance, so that was nice. But look at the audio, where we perturbed the audio and it went down almost to 0%. So this is good, and this is not so good, because it shows that in this incarnation of 2.5 Flash seems to be more vision heavy, and even a slight perturbation in the audio like led to a collapse of the collapse of the performance. Our suspicion was on like how these, maybe the late fusion of different modalities is leading to this behavior, but like again, hard to pinpoint for closed source models. Yes, Shiva.
So what are the outputs in the case when it's audio prompt? Did you see, does it correspond to the vision labels, or does it correspond to something else?
So the goal was it should correspond. Ground truth would be the new audio class that we added. There were some cases where it was getting confused with the vision. In some cases, it was a random class.
And the perturbed audio, is it audible and it's clear? Okay.
Yeah, it's of the same. So we tried to keep it at the same gain value, so it is as audible as the.
And did you also check what happens if you remove the vision at all completely?
Yeah. We I don't have it in the slides, but we had this study where we set all the frames to 0. So blank video, just audio, and the vice versa. Blank video, just the video, no audio. That was also not as good. And especially with the audio, and our theory there was the model has been trained to look at not just black frames, and that is probably leading to a deterioration in the performance.
I see. Or maybe in general, like this thing probably is a bad audio model, like 2.5 Flash. Do you think it's a bad audio model? It's like it seems to, even when you have vision component correct, right? When it is aligned, it's getting higher percentage. So it's probably, even in this case, it's not relying on audio at all.
It does, yeah. That is the suspicion. There is some other experiments where we tried to insert like attacking information, and Gemini 2.5 was easier to like attack from the audio angle. So that's the suspicion, that it isn't integrating audio. It's a very strong vision heavy and language heavy model. One more of the different combinations we tried. This is the case where we have aligned all 3 modalities aligned, and this is the case where we have we inserted a distracting text in the caption, just one word. And again, you see, notice that we explicitly tell the model focus only on the vision, and yet it takes a dip of close to 20%, and it's much larger for the audio. So this again, one phrase or one word seems to have overridden the entire like video plus audio evidence. So that was also like a very compelling finding for us. So there are a bunch more like scenarios that we studied where we completely hide each of these modalities or perturb 2 modalities at a time. So definitely check out the paper for all of these. But I wanted to get to like what we were sort of itching towards. Okay, we've seen all of these like systematic cases. It is struggling. How do we teach that, hey, like this is how this is a misaligned sample. Here is a sample that you should focus on, or here is a modality that you should focus on. A very a basic idea that we had was, how about we show the model or tell that, okay, this is what an aligned sample looks like. So this would have a label of 1. And this is what a misaligned sample looks like. So video of a bell ringing but a dog barking would have a label of 0. Video of a bell ringing and has the associated bell sound would have a label of 1. That's about it. 2,500 samples, just the last layer with like a LoRa, nothing fancy at all. So that led to like meaningful gains. So lots of numbers. Let's break this down. So we first saw that this is the one with the alignment aware fine tuning, where we first noticed that on the audio, where we saw that Gemini seems to struggle even in like baseline cases, this alignment aware tuning seems to have improved. Now let's focus on these 3 rows. So this is our base model, no alignment aware, and this is the one with alignment. You'd see that with teaching the model that what alignment and misalignment looks like, our hypothesis is that it learned to look at the right modality. It learned to look at vision when we were asking it to look at vision. It learned to look at audio when we were asking it to look at audio. So that led to like huge gains. Again, like in the paper, we've also shown the attention maps before and after the fine tuning, just again to validate this hypothesis that the learning is shifting towards the right modality. So if white box analysis is of interest to you, definitely like check that out. So it definitely surpasses the baseline, and also like in some scenarios the closed source models as well. Cool. This is my favorite finding. So we only told the model what a misaligned video and audio looks like, but took this model out of the box and retested it again on the text misaligned scenarios, and that led to like again like an improvement in the visual prompt question and also the audio prompt. Again, like the attention shifts also tended to indicate that the reweighting or readjusting of the attention to the right modality helped the text misalignment case as well. Okay, so this was work led by Tianle and Chaitanya. They had come up with the really interesting white box analysis. Lots of effort and hard work was put into this. Key findings: MLLMs struggle even when one modality is slightly misaligned. Text dominates, then followed by vision, followed by audio. And when modalities are under conflict, we know which modality to pick, more or less, but the models don't have that built in yet. Alignment aware fine tuning, which was a very simple trick, but that seemed to have really helped. We do want to test this on like other models as well, because we were only able to test this on Quen 7 billion, 2.5, to see if this generalizes across like different models.
So if I would like to take away some of these points and come up with attacks with other modalities, so most of the closed source models can bypass the attacks that we have, like the standard attacks. So if I want to put in attack from an image or audio, can I take, what would be the best way to do it?
Yeah, absolutely. That's a perfect segue into the next question, which is what we thought. If these models are so brittle, can we come up with like simple attacks and see what happens in that case? So this is where we were injecting benign misalignments, but take a case where These three look seemingly well. The image has Apple, the caption says Apple, but maybe I'd inject like a text saying B or something, and see what happens. So this is a typical typographic attack. Again, has been studied extensively in the image space. Sorry.
One more question.
Yeah.
So for the benchmark you just presented, I was wondering, would human performance on these misaligned examples just be 100% in this case? Or is it also something that would be harder for humans? So for the benchmark you presented, would the human performance on the misaligned examples just be 100%? Or were there also examples that would actually also be harder for humans?
That's a great question. So we did human study, and because the examples were so simple, like it's only like dog and then the dog, audio of the dog barking, the humans, it was a very easy task for them.
Maybe also for me, a very short question. Have you tried by any chance this bar raw example from the beginning on models?
We did not. That's a great point. We should. Yeah, I'm curious to see where we should try that. Switching to attacks, image typographic attacks have been there. People have extensively studied in the vision world. We tried to do multimodal attacks. So let's break this down. Image of video of a tiger, and the audio says the object that you're seeing is a tiger. And then we have our text prompt, which asks what is the object that best describes the content that you see in the video, blah, blah, blah. So that's the clean case. We'll again start with attacking one modality at a time. Here, we overlay a text that mentions a different animal, say a horse. We'll keep the other two modalities same. So we'll have a different object here, but then the audio says this is a tiger, this is a tiger, and then ask the question. What happens in this case? The visual prompt remained the same. We were again asking the model, look at the video, look at the object in the video and name what you see. What we are showing here is attack success rate. So how confident was the model in how easy was it to switch from tiger to horse? So this 50% indicates that out of 100 instances, 50 times the model was able to we were able to easily attack the model. So in this particular case, Gemini was more resilient. Well, this is okay because I mean, the text is right there, so maybe it's distracting. This was not that compelling an example for us. So we went, but one key takeaway that we have here is attack efficiency. It definitely depends on the underlying models capability. So stronger models, harder to attack than weaker models. But this is where things became more interesting. So we had the attack mode on for audio. So you have the audio where someone is saying this is a tiger, but then we would insert a whisper overlaid on top and say that the answer is horse or this is a horse. So this is a more sneaky attack. And then again, you could think of multiple combinations. Video would be clean, but only audio is attacked. Both are attacked. Different combinations are feasible. Keep the text clean because we want to ask the question in a clean way. And then we saw the same question. Look, what do you see in the video? Same model. Only thing that differed is the audio attack. So the success rate went from 5.8 to 9.27. So this shows that again, modalities are talking to each other and attacking one has an impact on the other. But this Quen had a huge we were very successful in fooling Quen because its attack success rate went from 50 all the way to 83. So now let's see, what if we ask the audio heavy question? But one finding here is that I attacked the audio, but it is also having an impact on the vision questions here. So have the same setting, but then we ask the audio question to it. And then we saw again like higher hit to Gemini, especially where having this whisper, the sneaky audio attack, led to a higher attack success rate for Gemini. So the takeaway from these different combinations is that audio attacks are sneaky, but they do have an influence on the vision only tasks as well. Is the setup and the finding clear? Yes.
So I was wondering here, the whisper that you add to the audio fragment, is it like, would it be to humans? Would humans be able to hear this whisper, or is it like barely detectable? And if you were to vary the detectability of this whisper, how does it affect the results?
Yeah, brilliant question, Bees. I don't have that exact slide, but we did do like a thorough analysis on like increase the volume and see at what point humans detect it, and then the model starts breaking. Takeaway was, so that's one on the volume. On position, like does it matter if I insert this whisper right at the beginning, right at the end? And also perception. So volume is different from perception, as you know. And we found that models can be attacked even before we can perceive that there is an audio to it. I'll share the plot with you, but yeah, there is that was our first concern, that well, if it's so audible, then maybe like it's obvious that the model will get attacked. But yeah, so takeaway here has been, attack one model, you would see the impact on like the other modality sensitive tasks.
Yeah. I'm wondering about the frame, because in the previous paper, you framed it as like aligned versus misaligned. Here it's attack, but it's still not like about safety as much, right? It's just like, again, alignment, misalignment. Or
It falls, yeah,
Yeah.
it is on the same bucket. We started off with, I think stealthiness was not the angle that we were coming. We really wanted to study the human should not be able to perceive it, but the attack should still exist, which is, I think, the visual example is not, maybe it's not coming clear, but we really wanted to see human as much as possible. We should not be able to detect that there is an audio attack or there is like a hidden text somewhere. Something that I was mentioning is this is sort of like sometimes could be a temporal flicker. So it shows up in like 2 or 3 frames and goes away. So sometimes humans tend to miss it, but then like the model did seem to get like attacked by it.
Okay, makes
Yeah,
sense.
great question though. Yeah. So again, like, why does this matter? This was the thought behind all of this was a bit worrying to see these models being deployed on some of these like safety critical like applications. So one thing we studied was, let's see if they are robust to some of these. So there is a data set called inappropriate prompts data set. It has prompts across like different categories, hate speech, self-harm, nudity, gun violence, etc. So we generated unsafe videos, but then inserted safe video, but saying that, okay, this is a safe, harmless, pleasant video, like, or variants of that. And again, attack success rate, lower is better. The baseline, should have named the model here. I think this was Quen. Baseline itself was easy to, it starts off having a high attack success rate, but just by perturbing the audio, by injecting that this is a safe video, led to like an increase in the attack success rate. So this again like warrants that. I mean, this is a critical application where you wouldn't want the model to make mistakes, and not perturbing the video at all and simply injecting this like fooling audio seem to have had a big impact on the attack success rate. We have a few more results in the paper on like different types of safety related like data sets, but yeah, it was consistent that this was the case. Okay, so the summary here is multimodal typographic attacks. Image only attacks have been studied, but we wanted to see if we can stealthily attack through audio and like temporal just like inserting it on in a few frames. It seemed to be the case that they were very brittle, and didn't cover it here, but yeah, there is an extensive study on stealthiness, human perception versus attack effectiveness, model capability. Does it do higher capability models like Qwen 30B? Is that better? Is that more resilient than Qwen 7B? And again, like if I keep repeating versus if I just say this is a safe video, does it have an impact? So again, studying different parameters of attack. Any questions?
Just also wondering, like on the state of the art models, do you think they have the shortcomings? Yeah, like that, and also the taking the audio and converting into text and using text as input.
Yeah, so on the first, we studied Gemini 3.1, and so Qwen struggles a lot. So Gemini is a bit more resilient, but it was easy to do that. On the text to speech and then pass it to so
Speech to text, maybe. Speech
sorry,
to...
speech to text. Yeah. So that haven't explored that. So maybe this is what
Is it common, like in the Omni model space? Is it more common to just directly use audio, or people are there studies showing that directly going through audio is better in general, or is it going through text is better?
Depends on,
for understanding, not.
yeah. So okay. So for understanding, the default is they convert audio to text because text is easy, stronger models compared to audio, which has like weaker models to begin with. But in reasoning and like there are some models that take video captioning as a task. So they do subtitles, the speech to audio, speech to text, vision, and also the audio. So they are trying to move towards using all modalities.
Sure. Thanks.
I think the existing content moderation, they're more text heavy, so they do what you said. So go from audio to text and then have a moderation model on it. Okay, so we've been talking and essentially ranting about MLLMs and the lack of robustness. So switching gears a bit to efficiency. This is a bit of a vision-centric few slides, but I think the fundamental principles are mathematical and are transferable across modalities. So let's see. So one of the interests is just making the generative models more efficient. So this was a few months ago. It takes WAN 2.1, which is a text-to-video generation model. Takes about 30 minutes to generate just a 5-second video. The reason, I'm sure all of you are familiar, is that diffusion, denoising is the underlying principle here. It's an iterative process. So during inference, you start from a pure noise image and you slightly reduce the noise, and that is very time consuming. And add that and temporal axes of like generating multiple frames, it just makes it very, very expensive. So the default is that every image is tokenized into equal size tokens, and then this diffusion is applied on each image. So this is the question, or this is the part that we focused on. The first is, every image is not created equally. Do you have to divide it into equal sized patches? Do you have to allocate the same compute to every token, every image, or every patch? So a very basic experiment is, instead of so Clip, VIT, any of these models you take, they have a default patch size of 4x4 or something. So we started off with using like larger size patches. Obviously, that brings down the inference time significantly, but then reduces the number of tokens. All of this is good news. But then look at the visual quality, the drop in the visual quality and the fine-grained details. So this is like very patchy and blocky compared to the high quality, like very sharp image. So just blindly increasing the patch sizes doesn't seem to be like the right way to go. So bringing back to the fact that all of these are generated using Runway, you see such diversity in the images. Focus on one particular image. Even in this one particular image, there are regions which have high texture. Definitely, that's where our eye gravitates to. We definitely need more tokens in that region. And there are certain other regions which maybe we can get away with using fewer tokens. So that was the underlying principle. Can we automatically determine what is a busy region or a region that requires more attention, and what are the regions where we can maybe get away with like larger patches and hence like fewer tokens? So that's one principle. So encode different regions differently based on their semantic complexity. So let's look at this, come back to this. Let's say we've figured out a way to solve that. We still have the denoising step where everything has to be generated iteratively, one step at a time. We asked again the same question. Do you need the same level of granularity at every time step? So it has been studied and established at this point that as the time progresses, the earlier denoising steps focus more on just painting out the higher level details. So just like the scene layout, very coarse level information. But as we come closer to the last fewer time steps, that's when the painting starts to get sharper, and then the diffusion focuses on filling in the finer grain details. So starts off with coarse information and then gets into like fine grained information. So the thought here is, well, the model itself has learned to go from coarse to fine grained. Can we somehow again use it for our benefit? So two questions, same answer. Every image doesn't need the same number of tokens, and every time step doesn't need the same number of tokens. So a key idea that drove this work is that, can I vary the patch sizes for every image and for every time step based on what's being evolved, like what the model is trying to generate. So this is the baseline where every time step, this is during training, every time step has the same amount of cost. And this is what we propose, where earlier time steps are extremely cheap, very efficient. And then as the painting starts to get less and less blurry, we start allocating the tokens that it truly needs. How do we get here? So this is our idea. looks nice on paper. How do we get here? A very, again, like a dumb thing that we tried was, well, it seems other papers, they have established that we can get away with larger patches in the earlier time steps and finer grained patches in the later time steps. Let's have this as our manual schedule and see what happens. The prompt was a very simple one, a red colored car. This is a baseline where every time step and every image had equal number of tokens. This is our image with like manual schedule. Now you see, I mean, it did generate the red car, but the nice textures, like the photorealism, all of that is gone. So manual scheduling is not going to give us what we want. So going back to this question, we had this through like empirically, we found that there is the reason why they need smaller, larger patch sizes in the earlier layer is because in the latent space, the evolution of the latent between time steps is a lot slower. So there isn't a lot of change that is happening between t equal to 1000 and t equal to 999 in the earlier layers when compared to t equal to 1 and t equal to 0. So there is faster, there is more information that is being changed in the later time steps than in the earlier time steps. Yes.
You think the other explanation could also be that you're more resilient to errors in the early stages, right? Like because at this point you have not decided what to draw. If it is text, if it is, I think that's the main thing. Like early on the trajectory, even if you go in a wrong trajectory, but that's still fine because it's very early on, and later on, once you determine what the image is, it's going to look like this cat. You don't have much more freedom to move around.
So. That makes a lot of sense too. That there is more room to like explore in the earlier stages in the latent space. The hypothesis was, so we measured this empirically, and we wanted to see if we can use that as a proxy to decide the times, the path size. So let's say we have. So I'm showing images, but we've been working in the latent space. So ZT-1, ZT plus 1, these are the latents at respective times T-1, T plus 1. We did finite order differences, just first order difference, which gives us displacement, second order gives us velocity, and third order acceleration. And acceleration is the rate of change of the displacement. And we tried to see if in a given small patch, if the acceleration is very small, then that means that the latent is evolving slowly. So we can get away with using a larger patch size. So I want to pause here to see if this made sense. So let's take patch size 2, the finer grain patch, to compute acceleration and see if for the patch size 2, let's say 4 pixels, if the rate of change of acceleration for these 4 pixels, is it high or low? Let's say it's very small, which means that all of these are evolving very slowly. So then we go and try the next larger patch size. So we go with patch size of 4. Now we have a lot more pixels, compute their acceleration, and see if their rate is smooth. Let's say it's super smooth. Let's say we are in a region where sky is being generated. So it's usually like a smooth region. So we go one step coarser and try with like a larger patch size. Yes. Yeah. Yeah, I heard the first part, I couldn't hear the second.
So the second part was, okay, so if you just take your steps, you wouldn't be questioning. Now, it's
So we are fixing the number of steps. It's still 50 steps. But then we are changing the granularity of the patch that the model is processing. And you're right that we had to add an adapter that makes sure that the model, by default, like you said, it was only processing patch size of 1 or 2. But now we had to add adapters to make sure that it can process 4 or 8 size. Did I answer the first one?
yeah, so the other one was, how do you compare this to having that step?
We have a few which benchmarking with like caching and also adaptive step size, and they did. Maybe give it 3 slides. I'll get to the findings where we have one. So hopefully the motivation has been clear. We wanted to adapt the patch size within an image and across the time steps, and we used the latent evolutions, the acceleration at which the latent is evolving as a proxy to decide at every step what patch size we should use. So this, again, like on 200 different text prompts, we tried to plot how the standard deviation is changing. So there is variance in the middle where that's where like a lot of that's where like the decision becomes very critical. But there is some general consensus that earlier time steps they don't need as much compute. So 3 examples where again this was a prompt zebra. You see that it's a highly text. Did you have a section? Okay, sorry. This is a highly textured image, which means that it did require a lot of, it did require a good number of steps with patch size 1 because high detail needs more compute. Look at this medium-ish image where there is texture here, but not as rich compared to that of zebra. So you do see, I should mention these along the y-axis is the patch sizes. You'd see how a lot of higher patch sizes are being used, patch size 4 and patch size 2. And this is an image which is again like void of like a lot of texture, which is the green one. And you notice how much compute we've saved by using higher patch sizes of 4. So by default, this approach was based on the content. So if the image needs high texture, if the prompt demands for high texture, we do allocate more compute. But I think getting the most in scenarios where you don't need to spend as much compute for like certain prompts. So some examples. Tcache is the one which caches the previous time steps and previous data. That's another like efficiency. That's another branch where people are trying to like speed up the inference, where they use caching of the previous time steps latent instead of recomputing at every time step. And Taylor's here, I believe, is the one which adapts the time steps. So this is the baseline where all time steps, all latents have the fine-grained image, fine-grained patch size. Notice that, well, from the outlook, maybe things they do look okay, but there is a shift in the object. It's not adhering to the prompt, or if I end up compressing more, then the loss of detail, like to the trace, is gone. And also here, I don't know if you're able to see, it's very blurry, like around the edge of the rim of the glass is very has blurred out a bit. But focusing on like ours, we were able to get 3.5x like compression, but also like maintain the object identity and also to not have like a perceived loss in visual quality. So another example, so DDIT is our, so dynamic DIT is our method. Taylor's here is the adaptive time step, and Pcache, if I remember, does the caching technique. Again, this is one of my favorite examples where they all look nice at the outset, but somehow the pose of the object changed. Not sure why, due to compression, and some of the fine-grained details you'd notice also went missing, like the tusks, the fine detail around the tusk. So we were able to extend it to video models as well. So this was WAN 2.1. There is WAN 2.2 now, but at that time we only had access to 2.1. So we were able to maintain the perceptual quality by while getting about 3x speed up. So baseline, just for context, is it uses the same amount of like everything, like all tokens and like all time steps use equal number of compute. So it does. It's not rosy. It has one good number of failure cases. We take the baseline and try to speed it up. So if the baseline fails to adhere to the prompt, then there's no, we can't come back from that. So that has been like a failure mode. If the 2 cats and 3 dogs are sitting, you see that the counting is wrong. So if we start here, then we won't be able to like get better. So that has been like a weak point of this work. So anyway, this is work led by yes.
In all these experiments, you're starting with a prompt and then a noisy patch or noisy image.
Yes.
The same noisy image for everyone.
Yeah.
Which is like surprisingly all the images look the same.
So
right.
Yeah, same. So the noise initialization is the same, and the seed for every model, like every parameter, is exactly the same, just to be able to not introduce any other variability. Yeah. So this was a work led by Tahiye. We are very excited and proud that this is a CVPR highlight this year. So again, the summary is not all time steps need equal compute. Look at the prompt, look at the image, and like this is again an inference time technique. So at inference, look at the previous latents, compute the acceleration, which was also cheap because it's just finite order differences to determine the right path size. And we were able to get significant compute gains both on like text to image, text to video models with limited loss of perceptual quality. So this is what we've been talking about. I have maybe one other, like just a teaser, and then we'll wrap it up. 2 research questions. One is understanding how these modalities talk to each other, assimilate information, and can we make each modality like more efficient, more robust in the way they're presented. So one recent work that we're excited is that, again, like when we're talking about multimodal models, and especially in the context of very long videos, extremely just there is so much temporal redundancy. And right now the default is to maybe sample every nth frame and feed it without looking at what information, what frame is being fed to. So something we tried was to fall back on, again, like the mathematical principles of Taylor sampling, which so where we use the past to predict the future frames or the future latents, and use that the error between the real information and the predicted information as a proxy for temporal surprise. So if in this particular case, so uniform sampling is the default in most MLLM models, where we sample every nth frame, 30th frame, 32nd frame, but it may not be capturing the most useful signal that's needed for the underlying task, or just representative of the video as well. So we compute Taylor residual, and anytime there is a very high residual, we tag that as, okay, this is a frame that has most temporally surprising data. So we retain that. And within the same constrained budget of small models, large models of like 8 frames or 32 frames, we show across 13 different tasks that we were able to sample the most informative frames that helped the even text-heavy prompts as well to get the right signal. So this is just like a visual. This is how the latent trajectory looks like. And when the frame changes, the scene changes, the latent shifts, but the Taylor prediction, because it only relies on the past, it continues in the similar method. So this we quantify as, okay, there is a temporal, something interesting is happening here. So let's catch that frame and use that for our BQA task, for our captioning task. So this is again like entirely test time. There's no training, nothing happening. Taylor series is again first order differences, so extremely fast to compute. We focused on long form videos because that's those are getting increasingly like the more and more long form videos, and just sampling every random frame is not the way to go. And again, like benchmarked across different models, different VLMs, and we saw that retaining the most informative frames definitely helps the downstream tasks. So this is where we started trying to understand different modalities. So this is the goal that we're working towards. Like, how do we make them holistically more efficient and not in a patchy band-aid way, but can we make it more unified in a holistic fashion while also keeping efficiency and robustness in mind? This is challenging for 3 reasons. One is, every time we start working on something to the time that we publish, there are models change. So have to make sure that we are keeping up with like different iterations of different models. So any solution that you build, it has to generalize across different model families. That's one key goal. Videos are getting richer and longer, and video is a very expensive like source of information, very useful. So it's important that we retain useful information, process videos more efficiently. Attacks are also getting stronger. Like 2 years ago, the kind of attacks that we were studying are entirely different from like the stealthy attacks that me and like several others are looking at. So we are approaching this from like multiple angles, but one angle that my group is very interested is again like exploring interpretability based tools. See how information is encoded in different layers, and understanding if that can be leveraged somehow to extract hidden knowledge and use it to improve the reasoning tasks. Another angle is we have to make this iterative. It cannot be a solution that like it's built, it's put out there, and then we move on to something else. Like models change, attacks change. So thinking of coming up with like a 2-agent situation where both are getting better and one helps the other continue to improve. So if any anything that I talked about resonated, like I'd love to hear your thoughts, your feedback. And again, yeah, thank you so much for being here and for attending.
Yeah, thank you so much, Deepti. Now we have maybe a few more minutes since we're already 11:40, maybe, I don't know, 3-4 questions. They're still remaining. Yeah, otherwise, really cool talk. We already had a lot of discussion also in between. Feel free to raise your hand now or online. I can also check if someone has a question. Yeah, there's one question.
Thank you. I have one question about the patching. So if my understanding is correct, so current algorithm is way dynamically adjust the size of the patching uniformly over one graph. But what if like we can do more customization, like for some dense area, and we do a more granular patching, and for the similar area like the sky, and we can hold the patch size constant. So would that give another layer of acceleration for
We fixed the patch size to be 8 or 2 or 1, but something that we didn't get around to in time was within a time step, we could also learn that's
yeah, so basically on one graph we can have different patch size. So would that further accelerate the
you could, yeah, definitely, definitely.
I see. So just the one.
Yep.
Yeah, cool work, by the way. Yeah. On the patching thing, can you talk a bit about the interdependency? So I was thinking, if you have one patch of a bigger size and a smaller patch next to it of smaller size, how does it interact? Because these are mutually dependent on each other, right?
So
In the network.
tied into your question, because within a time set, we fix the patch size to be like 4 or 8, but time step t and t plus 1. So we will just say time step t can have 4, and t plus 1 can have 2, and that was okay. But within the t, in this current world, it had to be like whichever is like the batch size that has the least standard deviation. Because it was again in time couldn't figure out how to like handle this discrepancy between like adjacent.
Yeah.
That's like something that's currently ongoing.
Okay.
Where as a next step to this, where because that we can squeeze out more efficiency.
Yeah. So in the current work, it's mostly a time step level.
Right. Yeah.
Oh, the another related point, like, did you also try like image editing? Like, I was wondering if you try image editing, and like we did a lot of work in this space. So you want to be faithful at many places, but then there are places where you have to do edits, and I wonder if this model figures out, okay, this is the patch where I have to have even fine-grained things, because you have to edit. It's not just reconstruction. It is reconstruction, but it's more complicated, I guess.
So you may be familiar with mirrors. Forgetting the name, but there is a work which image editing. Let's say you want, this is your image and you want to edit this region. So they add noise only in that region, and then they do the inference steps.
I see.
So that has shown to have like, but it's not efficient. That's the but answering the original question, we haven't looked at using this.
Okay. Any other questions? Cool. Maybe just one last broad question from me before we wrap up. I'm also very interested in mechanistic interpretability. I know that most of MechInterp comes mostly from the LLM side, and most of the tools were developed there. Do you think we can just adopt them mostly for multimodal vision, or do we need different tools or approaches?
So that's been the agenda, and the first question is like how much can be borrowed and transferred. We found success with sparse order tools, where we were able to read species on multi-modal like cross-dimensional layers and in like pure vision in diffusion models. So there is that is transferred. Logic lens has a different, not so much.
Yeah.
But yes, part of the people is
Okay, nice. Yeah. I have a better method in Logic Lens recently, like then that should work well for vision. Yeah. Okay. Thanks for coming, and see you I guess in 2 weeks. Next week is no T-Talk, it's Tech 8 conference.